Good day, everyone. I am J. Trisha F. Valiorimo together with Ms. Rosana Monzalez, Crystal K. Latina, Daisy Migallardo, and Mr. Rexy Jundurin, and we are the Group 9. My topic to discuss is all about the item analysis. If our students learned what we taught, we would never need to assess. It is only through assessment that we can discover whether the instructional activities in which we engage our students resulted in the intended learning. Assessment really is the bridge between teaching and learning. We can assess learners through a test, quizzes, or exam. Before we proceed to our discussion, let me present to you our learning objectives. Students are expected to develop an understanding about the concept of item analysis. Second, differentiate terms and ways on how to create and analyze students' responses on a certain standardized test. Third, distinguish concepts on how to measure an item and relate the concepts in a real-life situation of conducting a test. To understand item analysis, it can be done through first, planning of the test, which should be on designing the test and the preparation of the blueprint or the questionnaires. Then, we need to prepare for the preliminary draft, which are the item writing, editing, and the pre-tryout for learners. Then, after that, the examination proper or the conduct of the item test to learners so that we can process or measure the difficulty level and discrimination value of each item we made on the questionnaires. And that is the item analysis. After analyzing the results, we can now create or have a final draft and establishment of reliability and validity of the certain conducted tests. Item analysis is the act of analyzing student responses to individual exam questions with the intention of evaluating exam quality. It is an important tool to uphold test effectiveness and fairness. It is a statistical technique which is used for selecting and rejecting the items of the test on the basis of their difficulty value, discrimination power, and the distractors. The purpose of item analysis: first, to identify structural or content defects in the items. Second, to detect learning difficulties of the class as a whole. Third, to select the best available items for the final form of the test. Then, to identify the areas of weaknesses of students in need of remediation. Then, to increase instructors' skill in the test construction. Then, lastly, to identify specific areas of course which need greater emphasis or clarity. Therefore, item analysis is accompanied with these questions on determining learners. First, which topics are students struggling with? Second, do students really know the answer or just applying test taking strategies to eliminate the wrong answer? Third, does the item do an excellent job on separating students who know the content from those who may merely guess the correct answer? Then, is a particular question as difficult, complex, or rigorous as you intend it to be? Then lastly, which items should be eliminated or revised before use in subsequent test administration? Basically, item analysis reveals first, items that are too easy and too difficult. Second, items that failed to show difference between skilled and unskilled examinees, or how well it discriminated between high and low scorers on the test. Lastly, items that are scored incorrectly or misgraded, rather, whether all of the alternatives functioned as intended or the distractor analysis. The benefits of item analysis: it provides useful information for class discussion of the test. Second, it provides data which helps students improve their learning. Third, it provides insight and skills that lead to preparation of better tests in the future. Item analysis do have limitations, such as it cannot be used for easy items. Second, teachers must be cautious about what damage may be due to the table of specifications when items not meeting the criteria are deleted from the test, and these items are to be rewritten or replaced. Here are the steps in item analysis, which consist of 8 steps. First, score the test. These are the scores from the conducted test. Second, arrange the test papers from highest to lowest. Third, Separate the top 27% and the bottom lower 27%. 27% is used because it has shown that this value will maximize differences in normal distributions while providing enough cases for analysis. This was based from Wiersma and Jers 1990. Then the fourth step is prepare a tally sheet. Fifth, convert the frequencies to proportion. Sixth, compute for the difficulty index. And the seventh step is the compute for the discrimination index. And lastly, decide whether to retain, revise, or reject the item. Then here is an example of scores from the conducted test. So in this example, these are the scores from a conducted test which are arranged from highest to lowest that consist of 50 items and 50 students. In this case, the 27% of 50 is equivalent to 14 students. Therefore, we should pick 14 students who got the highest scores and 14 students who got the lowest scores, and the remaining scores will remain for the evaluation. The step 4 is the tally sheet. In creating a tally, the first row should be for the headings such as the item number, the upper 27% and the lower 27% of the students, where N is the number of cases, which is the number for the 27% of the 50. So, in this table, it shows the number of correctness of the learners in each item. Let's say, in item 1, the upper and lower score of students get it correct. Then, the second item, only 13 of the upper 27% students got it correct and 11 for the lower score of students. Then, for the third item, 14 for the upper and 11 in the lower, and so on. So, after the tally sheet, we should convert the frequencies or the number of correctness into proportions. So, proportions can be solved using the formula P is equals to number of correct answers over N, or the number of cases, or the 27% students from the upper and lower scorers. So, in this table, in item 1, we have 14 students who got the item correct from the upper 27% and the lower 27%. So, proportion is equals to 14 divided by 14 is equals to 1. Therefore, our proportion in the lower and upper 27% in item 1 is 1. Then in item 2, we have 13 correct answers from the upper 27%. Therefore, 13 divided by 14 is equals to 0.93. And in lower 27%, we have 11. So, 11 divided by 14 is equals to 0.79. Then in item 3, we have 14 correct answers in the upper 27% divided by 14 is equals to 1, therefore our proportion is 1. And in the lower 27%, we have 11 divided by 14 is equals to 0.79. And lastly, in item 4, we have 14 divided by 14 is equal to 1, and therefore our proportion is 1. And in the lower 27%, we have 7 correct answers divided by 14, therefore we have 7 divided by 14 is equals to 0.5. So, item difficulty. Is the exam question too easy or too hard? When an item is one that every student either gets wrong or correct, it decreases an exam's reliability. So, the percentage of students taking the test who answered the item correctly, the larger the percentage getting an item right, the easier the item. The higher the difficulty index, the easier the item is understood. It was based from Wood 1960. So, for example, if you have an item difficulty of 0.95, it doesn't mean it's extremely difficult. It means it's extremely easy because that 0.95 represents the fact that 95% of the students got it correct. So the difficulty index, or as the p-value, has a range of 0% to 100%, or more typically written as a proportion as 0.0 to 1.00 p-value. So the higher the value, the difficult the item. It can be interpreted using this criterion. So if the difficulty index is greater than 85%, therefore it is a very easy item. And when the difficulty index is greater than 70%, it is an easy item. And when the difficulty index between 30% to 70%, therefore it is moderately difficult to moderately easy. And when the difficulty index is less than 30%, it is difficult. And when it is less than 20%, it is very difficult. Now we have the step 6, it is to compute for the difficulty index. Computing for the difficulty index can be solved using the formula dFin is equals to P sub u plus P sub L over 2, where The DFIN stands for the difficulty index, and the P sub U is the proportion of the upper 27% who got the item correct, and the P sub L is the proportion of the lower 27% who got the item correct. So, in this table, it was based from the previous slides we solved on the frequencies and proportions of the upper and lower 27% scorers. So, in item 1, we have a proportion of 1 in the upper and lower 27% scorers. What we need to do is to substitute all the given proportion values to the given formula. So, the value of the proportion of the upper 27% is 1 and in the lower 27% is 1. Therefore, substituting those values is 1 plus 1 divided by 2 is equals to 1. Therefore, our difficulty index would be 1. And in item 2, we have a proportion of 0.93 in the upper and 0.79 in the lower. Adding it divided by 2, we have a difficulty index of 0.86. And in the item 3, we have 1 added by 0.79 divided by 2 is equals to 0.90. And in item 3, we have 1 plus 0.5 divided by 2 is equals to 0.75. Note that in computing for the difficulty index, what we only need to do is to substitute all the given proportion values in each item to the formula. So, next is the interpretation. From the previous slides, we solved about the difficulty index. And then, in item 1, we computed that the difficulty index in 1, therefore, it lies on the 0.91 above, therefore, it is very easy. And in item 2, we have 0.86. 0.86 lies on 0.76 to 0.90, therefore it is easy. And in item 3, we have 0.90, therefore it is also easy. And in item 4, we have 0.75, it is an average item. Next is the item discrimination. Thus, the exam question discriminate between students who understand the material and those who do not. Exam questions should suss out the varying degrees of knowledge students have on the material, reflected by the percentage correct on exam questions. So the interpretation of discrimination index may vary based on this range given in this figure below. Hence, the main purpose of discrimination index is to describe the ability of an item to distinguish between high and low scores, such as the scores of the upper and lower 27% of students after being ordered in descending way. So, the range of the discrimination index is from 0.0 to 1.00. The higher the value, the more discriminating the item. So, it is said that a highly discriminating item indicates that the students who had high test scores got the item correct, whereas students who had low test scores got the item incorrect. Item with discriminating values near or less than 0 should be removed from the test. This indicates that students who overall did poorly on the test did better on that item than students who overall did well. So the item may be confusing for your better scoring students in some way. 0.40 to higher is a very good discrimination, and 0.30 to 0.39 is a reasonably good discrimination but possibly subject to improve. 0.20 to 0.29 is a marginal or unacceptable discrimination which is subject to improve, and 0.00 to 0.19 is poor discrimination. This is to be rejected or improved by revision. So this is a negative discrimination index to be rejected. Next is the step 7. It is to compute for the discrimination index. Computing for the discrimination index can be solved using the formula DSIN is equal to the P sub U minus P sub L, where DSIN stands for the discrimination index and the P sub U stands for the proportion of the upper 27% who got the item correct, and the P sub L is the proportion of the lower 27% who got the item correct. So, in this table, from the previous slides of proportions and frequencies in the upper 27% and in the lower 27%, we need to substitute those proportion data or values to the formula of the discrimination index, such as in item 1, we have a proportion the upper and lower 27% as 1, therefore, P sub U minus P sub 1 is 1 minus 1 is equals to 0. Therefore, our discrimination index in item 1 is 0. So, in item 2, we have a proportion in the upper 27% as 0.93 and in the proportion of the lower 27% is 0.79. Therefore, substituting it to the formula, we have 0.93 minus 0.79 is 0.14. Same as in item 3, we have a proportion in the upper 27% as 1 minus to the proportion of the lower 27% as 0.79. Therefore, our discrimination index in item 3 is 0.21 and so on in item 4. Here comes the interpretation. As I have said earlier, the range is from 0.0 to 1.00. So the higher the value, the more discriminating the item. So from the table, we have this discrimination index in the item 1, we have 0. Therefore, it is low. Then in item 2, we have a discrimination index of 0.14. Therefore, it is also low. In item 3, we have a discrimination index of 0.21. Therefore, it lies on the moderate section. And in item 4, we have 0.5. Since 0.5 lies on the 0.41 and above section, therefore it is high discrimination value or high discrimination index value. Note that in assessing our future students, we need to use items that have high DI values or high discrimination index values in the test. Those are the testing's higher cognitive thinking abilities such as the comprehension, application, and problem solving. So, here comes the step 8. Decide whether to retain, revise, or to reject the item. So, when an item meets the general acceptability guidelines for difficult and discrimination, you should keep the item. If it falls outside the guidelines, you make a judgment whether to keep, revise, or reject it. So, it was stated earlier the different criterion of the difficulty index, the discrimination index, and here comes the decision making. So, when the difficulty index is moderate and the discrimination index is high and moderate, we need to retain the item. And when the difficulty index is moderate and the discrimination is low, we need to revise the item. And when it is very easy, difficult, and very difficult, in the difficulty index and in the discrimination index, it is high and moderate, we also need to revise the item. And lastly, if the difficulty index is easy, difficult, and very difficult, whereas the discrimination index is also low, we need to reject the item. Now we have the table based from our examples of the 50 scores that we solved in the previous slides. And now we have the value of the difficulty index and the discrimination index with the verdict. What we need to do here is to decide whether an item is to keep, revise, or to reject it. So in item 1, we have a difficulty index of 1 and a verdict of very easy. And in the discrimination index, we have a 0 which is low. Therefore, our decision would be to reject the item 1. And in item 2, we have a difficulty index of 0.86 and it is easy. And in the discrimination index, we have a value of 0.14. Since it is easy and low, this item would also be rejected. And in item 3, we have a difficulty index value of 0.90 and a verdict of easy. And in the discrimination index, we have a value of 0.29, which is moderate. Therefore, this item should only be revised. And in item 4, we have a difficulty index value of 0.75 and a verdict of an average. And in a discrimination index, we have a value of 0.5 and a verdict of high. Therefore, this item would be retained. Then, next is the point by serial correlation. So, point by serial correlation is used to correlate item scores with the score of the whole test. So, a special case of the person-product moment correlation where one variable is binary. So, there is a right versus wrong and the other is continuous or the total row test score. So, it can be done through steps. First, step 1 is to score the item as either right or wrong. And then step 2 is the use of point by serial correlation. Step 3 is the interpretation. For example, in this table, we have the item 1, 2, and 3 with 5 students, namely Anna, Chris, Hazel, Ben, Faith. So, note that the plus or the positive symbol means correct and the negative or the minus sign means incorrect. So computing for this point by serial correlation based on this table, we have simple formula as S is equals to R sub A minus R sub B over T, where R sub E is the number of pupils who got the item right after instruction, and the R sub B is equal to the number of pupils who got the item right before instruction. Then the T stands for the number of pupils who tried the item both. So note that the ideal value of S is 1 and the effective item fall between 0 to 1. Then the higher the positive value, the more sensitive the item is to instructional effect. Then items with 0 and negative values do not reflect the intended effects of instruction. So in this table, in item 1, we have a total correct after instruction is 5 and a total correct number before instruction is 0 based from the formula of S is equals to R sub A minus R sub B over T. We need only to substitute those given values as 5 minus 0 over 5 is equals to 1. Therefore, our teaching instruction is effective for item 1. And in item 2, we have 5 students who got a correct answers after instruction and 2 students before instruction. Therefore, substituting those values on the formula S equals to R sub A minus R sub B over T is equals to 5 minus 2 over 5 is equals to 0.6. Therefore, teaching instruction is effective for item 2. And in item 3, we have after instruction, we got 2 students who got correct, and before instruction, we have 2 students correct. Therefore, based from the formula, we have R sub A as 2 and R sub B is 2. 2 minus 2 is 0 over 5. Therefore, our teaching instruction is not effective for item 3. This only entails how effective your strategy in teaching to students. Hence, it connotes the idea that those items or those questions we made in each item need a remediation or in need to tackled again. And now we have the item distractors. For multiple choice exams, distractors play a significant role. Though exam questions effectively distract test takers from the correct answer, so for example, if a multiple choice question has 4 possible answers, or 2 of the answers obviously incorrect, thereby rendering the question with a 50-50% chance of correct response when distractors are ineffective and obviously incorrect, as opposed to being more disguised, then they become ineffective in assessing student knowledge. The distractors are important components of an item, as they show a relationship between the total test score and the distractor chosen by the student. Distractor efficiency is one such tool that tells whether the item was well constructed or failed to perform its purpose. So, here are the purpose of distractor analysis. First, it allows us to examine how many students in the upper group and the lower group selected each option in a multiple choice item. Second, we expect distractors to be selected by more students in the lower group than students in the upper group. And lastly, an effective distractor must be selected by some students. So note that any distractor that has been selected by less than 5% of the students is considered to be a non-functional distractor. So, for example, take the correct answer in this question. When the sum of the measures of two angles is 90 degrees, the angles are called A. Complementary angles, B. Adjacent angles, C. Line pair, and D. Supplementary angles. So suppose we have 110 students appeared in this achievement test. Then the first, we arrange the obtained scores of 110 students in descending order. And now, we have to select highest scorer on the upper 27% students and in the lower scorer 27% students, which is 30 students for item analysis based on the 27% of the 110 students. Note that any distractor that has been selected by less than 5% of the students is considered to be a non-functional distractor. So, reviewing the options can reveal potential errors of judgment and inadequate performance of distractors. So, these 4 distractors can be revised, replaced, or removed. So, in this table, based on the question or the item 1, we have here an options of A, B, C, and D. So, in the first row, we have the number in the upper group. Second is in the number of the lower group, and then the total of both students who answered from the upper group and in the lower group, then the percentage of selection, and in the discrimination index. So, in option A, which is the correct answer, we have a total of students who chooses option A in the upper group as 22, and in the lower group we have 9. So, in the total of 31, and then the percentage of selection among 60 students is 52%, and the discrimination index is 0.43. So, in option B, we have 3 in the upper group and 7 in the lower group, a total of 10, and the percentage of selection among 60 students 16.5%, and the discrimination index is negative 0.13. So in option C, we have 2 in the upper group, 8 in the lower group, and a total of 10, and the percentage of selection or the difficulty index is 16.5%. The discrimination index is negative 0.2. And lastly, in the option D, we have 3 in the upper group and 6 in the lower group, a total of 9%, and the percentage of selection is 15%, and the discrimination index is negative 0.1. Now, comparing it with the table, we can conclude that item number 1 is moderate and very good item. Hence, we can select it. It was based from the indices of difficulty and discrimination by Hopkins and Antis. And therefore, we can conclude that option A, or the correct answer A, has a moderate difficulty index and a very good item since it lies on the 0.30 to 0.70 indices, which is the discrimination index is 0.43. So, all the other destructors from B, C, D are selected by more than 5% of the students. So, obviously, destructors B, C, D can be considered as a fully functional destructors. So, here is the second example. What is the supplementary of an angle measuring 54 degree? So, choices is A, 36 degree, B, 126 degree, and C is 156 degree, and lastly D, we have 46 degree. And in item 2, we have also an options A, B, C, and D. First row is in the upper group and the second row is the lower group and the total number of students and the percentage of selection, then lastly the discrimination index. So, in option A, in the upper group, only 11 students who chose option A. And in the lower group, there are only 5, a total of 16, and the percentage of selection among 60 students is 26.5%, and the discrimination index is 0.2. So in option B, which is the correct answer, we have 28 students who chooses option B in the upper group and 12 students who chooses in the lower group, and a total of 40. So the percentage of selection is 67% and the discrimination index is 0.53. Option C, we have 0 or none value because none of the upper group and in the lower group chooses option C. And in the option D, we have 0 in the upper group and 4 in the lower group, a total of 4, and the percentage of selection is 6.5%, and the discrimination index is the negative 0.13. So, the destructors A and D are selected by more than 5% of the students, but the destructor C is selected by 0% students. So, obviously, destructors A and D can be considered as a fully functional destructor. So, but C is a non-functional destructor since it values 0. So, rather, it does not have a value. So, the item number 2 is very good item, but C is a poor destructor. So, we have to revise or replace the destructor to maintain the quality of the item. So, how can item analysis inform exam design? So, the data from item analysis can drive the way in which to design future tests. So, exams ought to measure the student learning gap as accurately as possible. So, note that in making a standardized test in our questionnaires as a future teacher, we need to examine each item through its difficulties, discrimination, and the distractors. So first, consider is the item difficulty level appropriate? Second, does the item discriminate appropriately? And lastly, are the distractors effective? These three questions underlies the reliability and the validity of an item we need. If you want further knowledge about this topic, you can browse ideas through these references. So that's the end of my discussion. The next reporter will follow. Thank you.
Good day, everyone. I am Rosani Gonzalez and I will be discussing reliability. So, what is reliability? Giving the same or compatible result in different experiments or situation is called reliability. So, by reliability of a test, mean how dependable, trustworthy, or faithful the test is. So, next is the definitions of reliability. The first one is Grunland and Lind. This refers to the consistency of measurement, that is, how consistent test score or other evaluation results are from one measurement to others. The next one is the Anastasi. This refers to the consistency of scores obtained by the same individuals when re-examined with the same test on different occasions or with different sets of equivalent item or under variable examining conditions. So we have here the four methods of reliability. The first one is the test-retest method. Second, split half method. Third, parallel forms method. The last one is internal consistency method. So the first one is the test-retest reliability. This is a measure of reliability obtained by administering the same test twice over a period of time to the same group of individuals. For example, a group of respondents is tested for IQ scores. Each respondent is tested twice. The two tests are, say, a month apart. Then the correlation coefficient between two sets of IQ scores is a reasonable measure of the test-retest reliability of the test. The next one is the split half method, a method of determining the reliability of a test by dividing the whole test into two halves and scoring the two halves separately. An example for this is, suppose we have a 20-item test in a reliability coefficient, so 0.16. Estimate the reliability of this test if 80 similar items were added to make it a 100 test. So the solution, in this instance, we have the formula K is equal to n sub 1 plus n sub 2 divided by n sub 1. So the value of n sub 1 is equivalent to 20 and n sub 2 is 80. So we will go to the distribution. The quantity of 20 plus 80 is divided by 20. And the final answer there, the final answer for the solution is 5. So that's why we come up to R sub 0 is equal to 0.60. Next is the third one, the parallel forms method. This is a measure of reliability obtained by administering different versions of an assessment tool. Both versions must contain item that probably the same construct, skill, knowledge base, and etc. to the same group of individuals. And we have an example. The questions are randomly divided into two sets, and the respondents are randomly divided into two groups. Both groups take both tests. Group A takes test A first, and Group B takes test B first. So the last one is the internal consistency method. The reliability is a measure of how well the items on the test measure the same construct or idea. So for example, if you create a quiz to measure students' ability to solve quadratic equations, you should be able to assume that if a student gets an item correct, he or she will also get other similar items correct. So that would be in the four method of reliability. Next is the importance. The importance of reliability is it determines the value of psychological test or study. If test results remain consistent, when researchers conduct a study, its reliability ensures value to the field of psychology and other areas in which it has relevance, such as education or business. So that would be in my part. Thank you for listening and God bless.
Good day, everyone. I am Crystal K. Latina, and I will discuss to you the measures of relationship. So, what is relationship? This is not what we commonly interpret as a relationship between two people. Let's talk about a relationship that is related to our topic today. Correlation coefficients are measures of the degree of relationship between two or more variables. When we talk about a relationship, we are talking about the manner in which the variables tend to vary together. So here are the examples of the measurements of relationship. The positive relationship, the negative relationship or inverse correlation, and no correlation. So if one variable tends to increase at the same time that another variable increases, there is a positive relationship between two variables. If one variable tends to decrease as another variable increases, we would say there is a negative relationship between the two variables. It is also possible that the variables might be unrelated to one another, so that there is no predictable change in one variable based on knowing about the changes of other variable. The scatter plots and linear relationship. It is a helpful way to visualize relationship between two variables. It is somehow related to graphing technique. Scatter plots represents each set of paired scores in a two-dimensional groups in which the dimensions are defined by the variables. For example, we are plotting and graphing scores of students in math exams to assist and determine students who lack of understanding and somehow still need of improvements in their learning and knowledge. By doing so, a teacher could find a way or new strategies to help improve the students' capabilities and enhance their critical thinking skills and problem-solving skills. Person product moment correlation. It was devised by Carl Pearson in 1895 and it is still the most widely used correlation coefficient. So, Pearson product moment correlation is an index of the degree of linear relationship between two variables that are both measured on at least an ordinal scale of measurement. You may see in the picture below the ordinal scale of measurement. From 0 to the left is a perfect negative relationship, while on the other hand, the 0 to the right is a perfect positive relationship. Spearman rank order correlation. It provides an index of the degree of linear relationship between two variables that are both measured on at least an ordinal scale of measurement. It is the same range 2 as the Pearson correlation, and the number also mean the same thing. We can also derive it using the Spearman ranks formula, which is the R sub S is equals to 1 minus 6 summation of V squared over N quantity of N squared minus 1. That's all. Thank you.
Good morning, everyone. I am Daisy Gallardo and I will discussing to you about the coefficient of determination. Learning objectives. First, to learn what the coefficient of determination is. Second, how to compute it. The coefficient of determination is a number between 0 and 1 that measures how well a statistical model predicts an outcome. Interpreting the coefficient of determination. Coefficient of determination or R squared. 0. Interpretation. The model does not predict the outcome. Between 0 and 1, the model partially predicts the outcome. And 1, the model perfectly predicts the outcome. What is the coefficient of determination? The coefficient of determination or R squared measures how well a statistical model predicts an outcome. The outcome is represented by the model's dependent variable. The lowest possible value of R squared is 0, and the highest possible value is 1. Put simply, the better a model is at making predictions, the closer its R squared will be 1. Example. Imagine that you perform a simple linear regression that predicts students' exam scores or dependent variable from their time spent studying and dependent variable. If the R-squared is 0, the linear regression model doesn't allow you to predict exam scores any better than simply estimating that everyone has an average exam score. If the R-squared is between 0 and 1, the model allows you to partially predict exam scores. The model's estimates are not perfect, but they are better than simply using the average exam score. If the R-squared is 1, the model allows you to perfectly predict anyone's exam score. More technically, R-squared is a measure of goodness of fit. It is the proportion of variance in the independent variable that is explained by the model. Graphing your linear regression data usually gives you a good clue as to whether its R-squared is high or low. For example, the graphs below show two sets of simulated data. The observations are shown as dots. The model's predictions, the line of best fit, are shown as a black line. The distance between the observation and their predicted values or the residuals are shown as purple lines. You can see in the first data set that when the R-squared is high, the observations are close to the model's predictions. In other words, most points are close to the line of best fit. Note, the coefficient of determination is always positive, even when the correlation is negative. In contrast, you can see in the second data set that when the R-squared is low, the observations are far from the model's predictions. In other words, when the R-squared is low, many points are far from the line of best fit. Calculating the coefficient of determination. You can choose between two formulas to calculate the coefficient of determination, or R-squared, of a simple linear regression. The first formula is specific to simple linear regression, and the second formula can be used to calculate the R-squared of many types of statistical models. Formula 1. Using the correlation coefficient. Formula 1 is equal to R squared is equal to quantity R to the power of 2, where R person correlation coefficient. Example, you are studying the relationship between heart rate and age in children. You find that the two variables have a negative person correlation. R is equal to negative 0.28. This value can be used to calculate the coefficient of determination, R squared, using Formula 1. R squared is equal to quantity R to the power of 2 is equal to R is negative 0.28 to the power of 2 is equal to 0.08. Formula 2, using the regression outputs. Formula 2, R squared is equal to 1 minus RSS over TSS, where RSS, sum of squared residuals, TSS is equal to total sum of squares. Example, as part of performing a simple linear regression that predicts students' exam scores or dependent variable from their study time independent variable, you calculate that our sum of squared residuals is 629.22. Our total sum of square is 2187.04. These values can be used to calculate the coefficient of determination R squared using Formula 2. Our formula is R squared is equal to 1 minus RSS over TSS. 1 and our RSS is 629.22 over RTSS is 2,187.02 is equal to 0.29. So 1 minus 0.29 is equal to 0.71. Interpreting the coefficient of determination. You can interpret the coefficient of determination R as the proportion of variance in the independent variable that is predicted by the statistical model. Other way of thinking of it is that the R is the proportion of variance that is shared between the independent and dependent variables. You can also say that the R is the proportion of variance explained or accounted for by the model. The proportion that remains 1R is the variance that is not predicted by the model. If you prefer, you can write the R as a percentage instead of a proportions. Simple multiply the proportions by 100. R squared as an effect size. Lastly, you can also interpret the R as an effect size, a measure of the strength of the relationship between the dependent and independent variables. Psychologist and statistician Jacob Cohen, 1988, suggested the following rules of thumb for simple linear regressions. R squared as an effect size. Minimum coefficient of determination or R squared value. 0.01 effect size interpretation is small, 0.09 medium, and 0.25 is large. Be careful. The R squared on its own can tell you anything about coefficients. Example, interpreting R squared, a simple linear regression that predicts students' exam scores dependent variable from their study time independent variable has an R of 0.71. From this R value, we know that 71% of the variance in students' exam scores is predicted by their study time. 29% of the variance in students' exam scores is unexplained by the model. The students' study time has a large effect on their exam scores. Studying longer may or may not cause an improvement in the students' scores. Although this causal relationship is very plausible, the R alone can tell us why there's a relationship between students' study time and exam scores. For example, students might find studying less frustrating when they understand the course material well, so they study longer. So that will be all my part. Thank you and God bless.
Good day, everyone. My name is Roxijon A. Loren, and today I'm going to discuss about the inter-rater reliability. So what is inter-rater reliability? Inter-rater reliability is a measure of consistency used to evaluate the extent to which different raters or judges agrees in their assessment decisions. It answers the question, is the rating system consistent? Simply, inter-rater reliability measures the level of agreement between raters or judges from the same individual event or person. So, examples of the inter-rater reliability is the judging of a beauty pageant and the conducting a job interview and also the scientific symposiums. Inter-rater reliability can have a high or low values. So, a high inter-rater reliability values refer to a high degree of agreement between the examiners, while low inter-rater reliability values refer to a low degree of agreement between the examiners. So, if everyone agrees, the inter-rater reliability is 1 or 100%. And if everyone disagrees, the inter-rater reliability is 0 or 0%. High inter-rater reliability indicates that the raters' rating for the same item are consistent. Conversely, Low reliability means they are inconsistent. Ratings data can be binary, categorical, and ordinal. Example of these ratings include the following. So first is the inspectors rate parts using a binary pass or fail system. The second is the judges give ordinal scores of 1 to 10 for ice skaters. And the third is doctors diagnose diseases using a categorical set of diseases names. So, there are methods in measuring the inter-rater reliability. So, first is the percent agreement. Percent agreement is simply the average amount of agreement expressed as a percentage. So, we have here the formula for the inter-rater reliability for the percent agreement. So, inter-rater reliability is equal to the number of agreements over the number of possible agreements. So, we have here an example for the percent agreement. Suppose two judges are asked to rate the difficulty of 10 items on a test from a scale of 1 to 3. The results are shown below. So, from the table below, we can see in the first column are the 10 questions or the 10 items of the test. In the second and the third column are the rates of the two judges rating each of the questions or the items. For each question, we can write 1 if the two judges agree and 0 if they don't agree. So we can write this in the fourth column. So based on the table, the number of agreements between the first judge and the second judge are 7. So this means that they agreed in 7 questions or items in terms of its difficulty. So now that we have the result, we can now solve for the inter-rater reliability with the formula number of agreements over number of possible agreements. So our number of agreements is 7 and our number of possible agreement is 10. So 7 divided by 10 is equal to 0.7 or 70%. So we just multiply 100 to 0.7 to convert it to percent. In interpreting the result in percent agreement depends on the field the assessment was held. In general, an inter-rater reliability of at least 75% is required in most fields for a test to be considered reliable. On the other hand, an inter-rater reliability of 95% may be required in medical settings. So going back to our example in the percent agreement, so the result is 70%, which indicates that it has a low reliability, which also means that the raters' ratings are inconsistent. So we have here another method in measuring the inter-rater reliability. So it is the Cohen's kappa. Cohen's kappa calculates the percentage of items that the raters agree on while accounting for the fact that the raters may happen to agree on some items purely by chance. So, Cohen's kappa is the more difficult way to measure the inter-rater reliability. The interpretation of kappa result are as follows. So, when the value is 0, this indicates that there is no agreement. When the value is between 0.10 to 0.20, this indicates that there is a slight agreement. When the value is between 0.21 to 0.40, this indicates that there is a fair agreement. When the value is between 0.41 to 0.60, this indicates that there is a moderate agreement. When the value is between 0.61 to 0.80, then this indicates that there is a substantial agreement. When the value is between 0.81 to 0.99, this indicates that there is a near perfect agreement. And when the value is 1, so this means that there is a perfect agreement. The formula for Cohen's kappa is calculated as K is equal to the quantity of P sub O minus P sub E over the quantity of 1 minus P sub E, where P sub O is the relative observed agreement among raters, and P sub E is the hypothetical probability of chance agreement. Cohen's kappa always ranges between 0 and 1, with 0 indicating no agreement between raters, and 1 indicating perfect agreement between raters. We have here an example. The following hypothetical data comes from a medical test where two radiographers rated 50 images for needing further study. The researchers A and B either said yes for further study or no, no further study needed. 20 images were rated yes by both. 15 images were rated no by both. Overall, rater A said yes to 25 images and no to 25. Overall, rater B said yes to 30 images and no to 20. So, calculate the Cohen's kappa for this data set. To calculate the Cohen's kappa, the first step is to calculate first the P sub O, or the observed proportional agreement. So, based on the data set, there are 20 images that were rated yes by both. And there were 15 images that were rated no by both. So, the formula in finding the P sub O is equal to the number in agreement over the total. So, we just add the 20 images that were rated yes by both and the 15 images that were rated no by both. So this is our number in agreement. And for our total, so this is the total images. So the total images is 50. So we add the 20 plus 15, which is equal to 35, and divide it by 50, resulting to 0.70. The next step is to find the probability that the raters would randomly both say yes. Rater A said yes to 25 over 50 images, or 0.5 or 50%. Rater B said yes to 30 over 50 images, or 0.6 or 60%. So the total probability of the raters both saying yes randomly is 0.5 times 0.6, which is equal to 0.30. For the third step, we will calculate the probability that the raters would randomly both say no. So rater A said no to 25 over 50 images, or 0.5 or 50%. Rater B said no to 20 over 50 images, or 0.6 or 40%. The total probability of the raters both saying no randomly is 0.5 times 0.4, which is equal to 0.20. For the fourth step, we will calculate the P sub E. So, we'll just add the answers that we get from step 2 and step 3 to get the overall probability that the raters would randomly agree. So, P sub E is equal to 0.30 plus 0.20, which is equal to 0.50. And now for the last step, we'll just substitute the values of P sub O and P sub E that we got from the previous steps. So, using the formula K is equal to the quantity of P sub O minus P sub E over the quantity of 1 minus P sub E equals to the quantity of 0.70 minus 0.50 over the quantity of 1 minus 0.50, and is equal to 0.20 over 0.50. So our final answer is 0.40. So this indicates that there is a fair agreement based on the interpretation on the coins kappa. So that's the end of my discussion. Thank you everyone for watching and listening.